Did you draw a picture? I will tell you on this one, it helps to draw the picture kind of exaggerated. Otherwise, if you try to draw it how it really is, I mean, you couldn't even tell what you're looking at. So, what should I draw first? He said tower. What did you say, circle? Anybody else? Alright. I really like this problem, number one, because it's kind of cool to think that you can calculate the horizon, like the distance to the horizon. Has anybody ever stood on the beach and looked out where you can see the sky and the water meet? Okay. It would be kind of like that. I mean, we have mountains and cliffs and hills, so it's kind of hard to get a good visual of the horizon, right? Or the horizon is the mountain, so we don't have the same scenario. Has anybody ever been to the Willis Tower? I haven't either. I don't know where it is, but it kind of looks like the one in Chicago, I think. I'll check, but anyway, point is, like when you're that high up looking out over, you can kind of see a clear horizon better, right? So, we definitely need the Earth, since it's talking about the Earth. And it says the 103rd, the 103 doesn't matter. Why? Like in terms of like sifting through information given in a problem, why doesn't that matter? What was that? Yeah, like that's just telling us kind of where in the building, but we have a number here that's better. That's the distance or the height that she is off of the ground, okay? So that's, I guess you could call that kind of a distracting number. I mean, it's interesting. That's way up there. Has anybody ever been in a skyscraper before? If you ever get a chance, it's kind of an interesting experience to be way up there and looking out. Knowing you're in a building that's not that big. You know, like width-wise and stuff. Okay. It does talk about the Earth's radius, so let's put that on here. And it's in kilometers. Units are important in this one because, well, you're first noticing what? What's different about these two? Yeah, so that's a mismatch already that we're going to have to address. Either put it in meters or kilometers, but they can't be different. All right, so there's kind of the obvious stuff from the picture, or from the description. So what are we doing from there? What's actually happening in the real world? Her standing at this window at the 103rd floor, looking out to the horizon, and then how does that look in a math problem? What can we add to the picture? Any other thought? Okay. Anybody else? Okay. Well, let's stick the building on here somewhere. I mean, can I stick the building right here? That wouldn't really work, right? Not for the math solving. Plus, can she see the horizon? Like, I want to connect it to my radius, in other words. Okay? So maybe like draw it like right here. Now this is the exaggerated part. Is the building actually going to stick out that much? No. Okay? But it gives you an idea of what you're looking at. And so now she's looking, you can draw it either way, but she's looking and just touching the horizon. Okay? That's like your view stops at the horizon. So I'm not going to draw it continuing past. I'm just going to draw it connecting right there like that. Okay? Because then the Earth curves past out of your field of view, is why. All right. So just because I drew my red building in the line of sight a little differently, I need to connect this radius to the end of her line of sight. And what's going on right where those two meet? Where she sees the edge of the horizon, what's going on right there? That's 90. Why? Because that's tangent radius, right? The line of sight to the horizon is a tangent line. because we can spot that point where it disappears. Okay, and then it kind of looks like we're forming a what? A triangle, yeah. So we need to go ahead and add this in here. And how long is it? So the blue line, the radius is 6,400 kilometers. How long is the red line? What? To there. Right? It's 6,400 kilometers to the surface. Plus 400 meters more. Right? So, again, we can't put 6,404 or 6,800 because those are different units. So, do you want to work in kilometers or meters? You need to decide that. I already wrote this one in kilometers, so I would stick with that myself, but you're welcome to switch. So, here's how I'm going to write it. This is 64, but what is that? In kilometers, what is that? What is 412 meters specifically as kilometers? Do you guys remember what kilo means? Do you remember this metric prefix thing? This is a side note. This is just for fun. Kilo, hecto, deca, base, deci, centimilli. Do you remember those? You never learned them? Well, what? Have you heard of this is King Henry? Have you heard the way to remember it? You've heard that. What's the rest of it? King Henry.
Doesn't?
Died.
Oh.
Doesn't breathe. No. The usual one you hear is King Henry died by drinking chocolate milk. You heard that?
No, never.
Okay. I had some students once that came up with King Henry died by doing crystal meth.
Okay. That's better.
He was a bad King Henry. Well, anyway, this stands for base, like meter is a base unit. And then deca is 10, hecto is 100, kilo is 1,000. So going bigger, this would be like a decameter would be 10 meter sticks, hectometer would be 100 meter sticks, and a kilometer or a kilometer is 1,000 meter sticks. And it's all just powers of 10. Like the metric system is so much more smart than ours. And then it goes the other way, like 1/10, 100, 1,000. You've heard of like a millimeter, right? We talked about that. That's all. That helps you remember those. So a kilometer is 1,000 meters. So what fraction of a kilometer is 412? 412 out of 1,000, right? Which is what? Do it on your calculator if you don't know. .412. Okay? So did we really add much to this? No. Like in the scheme of the whole radius of the Earth, we added 0.4 kilometers, which is nothing compared to 6,400. But it's enough that we know that we can see the horizon, and it's enough to give us x, the distance to seeing it. Okay, so I would zoom in on that triangle now. And we have 6,400, we have 6,400.412, and we have x. How are you going to solve for x? Yeah, so if you haven't done that, go ahead and solve for x with the Pythagorean theorem. And you give you about 1 minute. Okay, so on this one, obviously we're glad we have a calculator because the numbers are big. But it's just subtract 6,400 squared and then square root to get x by itself. So combined a couple steps there. Alright, why am I on that? Square root. of 6400.412 squared minus 6400 squared is 72.6. Is that surprising? That for such a tiny little difference, it makes 72 kilometers difference on the horizon. So in miles, how many is, anybody know how to convert kilometers to miles?
No.
So multiply that, take your calculator and multiply that by 0.62. What was it?
45.012.
Okay, we'll just call it 45. So it's about 45 miles away, which is pretty far, right? So if you're at the top of this building at Central, if we put a building like that here, we could see 45 miles to the roughly. You know, again we have mountains and stuff, but if we looked west, which is where they're the lowest, you could see. I don't know. That would be
More mountains.
clear out to past like Mac, headed toward Utah. If it wasn't elevated again over there. Cool. How high up are you if you're 412 meters? Is that to convert to feet from a meter? Do 412 times, what do you think? Like, how many feet are roughly in a meter? Yeah, it's roughly 3, right? It's one of those meter sticks is a little bit longer than a yard. So it's actually 3.28 feet per meter. So how many feet is she up there?
1,351.3.
Okay. That's pretty high. Anybody ever go to the monument? How deep is like Ute Canyon? Like Cold Shivers Point when you look down? Anybody know? I don't, it's not that deep.
It's over.
That would stick way up out of there. What? What? You're up to something.
Even with that, I couldn't anyway.
So what do you, when you look at these pictures, what do you describe a chord as? What would you say? Okay, it does do that. She said it's a line that separates a segment from the circle, the rest of the circle, which it does do that. All right, so you can see tangent goes flying past the circle and touches once. How many times does a chord touch? 2 times. Okay, so what's the difference then between a chord and a secant that touches twice? The secant keeps going, yeah. Or is that what you said, passes through? Yeah, whereas a chord stops. It's just on the circle and then it doesn't keep going. Which seems kind of like, well, why do we have to distinguish? But there's different things we can do with either one. So I'm going to start a new page even though I had a box left there. I think we'll just put it all together. The reason why is because chords have, I think it's 5 or 4 different theorems. That, you know, tangents we had 2 theorems. Tangent radius was 90. Tangents from the same point were congruent. So that was 2 theorems. Chords is going to have 4 or 5. Huh? No, there's only 2. There's only 2. 1, 2. Well, that's not a theorem, that's a definition. So, these are the theorems. All right.
That's a cool point.
So there's 2. I have to add one more thing on here. All right. Chords.
Do you want us to move to second page?
Well, you can decide because sometimes students are not, they write smaller than me, so maybe you have a couple more. I'm going to have a definition box with the picture, and then, like I said, I can't remember if it's 4 or 5, I'll look at here in a second, but, so that's going to be like 4 or 5 boxes of stuff. I just like to have it together, that's all. You guys basically defined what a chord is, kind of by looking at the picture. So it's a line segment with end points, and here's kind of the key word. So I'll make it big, on the circle. Guys, do you remember how we notate a segment, no matter if it's in a circle like this or a triangle or anything else? The notation for a line segment. Sometimes we call it side length. Okay. So let's draw some and I think it'll come back to you pretty fast. Like if we connect those 2 points, we call them AB, that's a chord. And then we just do the line above the 2 letters. Remember that? We've seen that a whole bunch. Okay, you can put another one in. And maybe call that, of course, CD. These can go kind of all over in the circle, all over the place. So here's an interesting fact, that the diameter is a special chord. Why would we call it a special chord? What does the diameter do? Yeah, it divides the circle in half. So like the arc measure are split in half. The area is split in half. Also, it goes through the,
Central point?
Yeah, it goes through the center of the circle, right? But it still has its endpoints on the circle, so it's a chord. Okay, now we can't do a whole lot with these until we start writing about the theorems, like what about them. So, but before I do, you guys we'll come right back to that. Let me just show you a couple of these. So chord BC, chord EF. What do you think is true about those two? In this case, I mean. He's saying congruent. Why?
You know that angle D and A and our radius E to D and B to A.
Yeah. Congruent circles, right? Because they have the same radius. Congruent central angle, that's 123 is the central angle. Why is it a central angle? It's at the center. Our next topic, I'm being specific about this because our next topic, we're going to have like an angle over here on the side, which is different, okay? So make sure you know it's because it's at the center. Anyway, so yeah, those are definitely congruent chords. I'm going to mark them as that. What would make that chord shorter? Like, what's a way to make it shorter?
Longer or
Okay, like a bigger circle? Is that what you're saying?
yeah.
It's almost a perfect circle.
I'm almost a perfect dude. No, I'm just kidding. I'm very far from that. So I kind of think if we make those longer, that the chord would be
I
longer.
guess making the angle shorter,
Okay. So kind of thinking like
closing it, yeah.
closing it a little bit. Yeah. Good. And then how would we make that bigger in the same circle? How would we make that bigger? The chord. How could we make in the same circle? How could we make the chord bigger?
By making the angle.
Yeah. So it's very angle dependent, right? And you can even see it if I just do it with my hands, like an angle like that. The chord is very short and then bigger. Okay. So it's really mostly dependent on that angle. So if I told you that two chords have the same central angle in congruent circles, what would you know about the chords? They're the same, right? So that's one of our theorems. Here's another one. Let's say I tell you that's 5 or whatever circle we're drawing here. And that's also 5. What do you think is true about those two? Chords, I mean. I'll put some letters. Yeah, it seems like if they are both drawn in the same circle or congruent circles, meaning I could copy paste, if they're the same distance away, doesn't that set the angle, right? Okay. Because if I'm talking about being out here, that is a different central angle and it's farther away. So they're very connected, okay? So that's another theorem. And let me show you some better pictures. Okay, first one, and there's tons of words on here, so we're going to shorten them down. I don't want you to worry about all that. But basically, if two chords are congruent, their central angles are. We saw that one. If two arcs in a circle are congruent, their chords are. So remember, an arc is this piece and that piece. Doesn't it make sense that a congruent arc should have the same cutoff points, if you want to think of it that way, that make the chord, right? Okay. Here's a couple more. This is what I was just saying. Chords that are equidistant, meaning the same distance from center, then they are congruent. Any issues with that one? Okay. And then diameter or radius, if it's perpendicular, it bisects the chord. What does the word bisect mean? Do you remember that one? Splits it in half. So again, if we're perpendicular, I'm going to draw this a little bit less busy than that. Here's some chord, and we're being perpendicular to that. Wouldn't you agree that these are both radiuses, which makes that triangle isosceles? And then the altitude bisects the chord. So if we think back to triangle stuff, it makes sense. Probably more so than circle stuff. That's all that one's saying. Okay, so there's the 4. And then this one's a little bit less useful. I'm not sure we'll even write it, but basically if we're bisecting a chord perpendicular, it's got to go through the center. That's all that one says. And that kind of makes sense because you can't bisect something if you're like over there, right? That's all that one's saying. So do you think numbers would help, or do you want to just write? I think description is probably more helpful. Okay. And these are not in any particular order. So chords equidistant from center. What does equidistant mean? Same distance. Here's the wording of the theorem somewhat. So if chords are equidistant from the center, then they're congruent. And of course we'll draw a picture to show that. Tell me if I need to move so you can see. Okay, so those are congruent chords because we better put some letters on here. So AB is congruent to CD, and we're showing that the distance from center is the same. Although my picture isn't super good at showing it. What was true about chords and central angles? Okay. If two chords are congruent, what's true? Then their central angles are congruent, right? We said it depends how big or small the central angle opens, kind of thinking, determines how big that chord is. On this picture, make sure you note that the angles are congruent. And the chords are too. Is there a dog? Why is there a dog?
Sounds like shoes on the floor. Yeah, those shoes.
Is that a dog?
What?
Did I hear a dog barking?
Hear one?
Oh, okay.
Sorry.
We're just, yeah, in here,
Yeah.
we heard a dog.
Oh, yeah, it might be that.
All
Let's go take a look.
No, I feel like shoes
right.
across the floor.
Here's, you don't need to go anywhere, just stay there, but here's a good way to use that one. So maybe if I tell you this chord is, I'm just going to make up some number, 50, and I ask you how long is this chord? And that's all I give you? What would you say? How big is X? It's also 50. How do we know though? Because, there's nothing connecting that chord to that chord at this point. But remember vertical angles? Vertical angles based at the center point can translate chord values across, because chords with the same central angle are congruent, or we can say congruent chords have the same central angle. So either one. But that's a way to use that one, or at least to keep your eye out for that one. Okay? Alright, next one. Chords. Can I put that all the way, like, is that, okay. So chords and arcs. There's a lot of congruent stuff with chords, right? So if two arcs are congruent, then their chords are congruent. Now when we talk about congruent arcs, are we talking about arc length? Or what was the other one? Arc measure. Which one do you think we're talking about? It is arc measure, yeah. And that's, I mean, you can think about the fact that, remember, central angle is the same as the arc measure in degrees. So it makes sense that this theorem kind of flows from that. But it might be a good idea to just kind of put in parentheses arc measure. But is it just arc measure? Here's what I mean. Let's say I define some arc. Don't put this on your picture, I'm just talking through it with you. And then of course it makes a chord. Isn't that length of that arc dependent on the central angle, right? Theta at a 360. So if I had another arc over here with some chord and it had the same length, in the same circle or a congruent circle wouldn't have to have the same central angle. And if it has the same central angle, then it's congruent. So it's really measure or length. Thinking about the fact that you can backtrack the angle from the length, right? Okay. Anyway, let's go draw a picture now. If you have a highlighter or some way to highlight, it's probably going to be a little easier to show that we're talking about the arc. And then don't forget to mark congruent chords. Do you think we can show congruent arcs with like a tick mark like that? I don't think we've seen that. Do you think it's okay? You will. It is okay, and you might come across that. Actually, probably will come across that in some of your work. So. All right. I think we'll just write one more. Now it's too close. So if a radius or diameter is perpendicular to a chord, it bisects the chord. Alright, I'm going to make sure everybody's with me on the picture because these problems come up a fair bit in terms of solving for various lengths. And this is a pretty commonly used theorem for those kind of problems. And like all the rest of these, basically it was like copy-paste congruence, right? But this one is going to set up what kind of triangle? Yeah, it's a right triangle. In fact, probably should put just a reminder that that means 90 degrees. So now we're going to write triangles and it will set up scenarios where we solve. Can I stand here and draw?
No.
Okay, so drawing your chord. It doesn't have to be just like mine in terms of where you put it. But. Okay, does the radius stop at that chord when we go to draw it? No. So the radius or diameter, either one, is going to go all the way to the edge of the circle. So let's finish drawing and then I'll tell you a couple things. So what's congruent is this, but we have to make sure to put in that it's a 90-degree angle. Otherwise it's not necessarily, actually it's not. If it's not a 90-degree angle, it doesn't bisect and the segments aren't congruent. Okay, so that's the theorem we just wrote. Let me show you how we typically use this to solve. So add to your picture a radius connecting to each end of the chord and label it R. So do you see an isosceles triangle form? Okay. And so sometimes we want to solve for that little piece that connects the center to the chord. So you could maybe like put an X there, something. So I'm going to just say we often solve like this, where we set up this triangle. Maybe we're solving for the length of the chord with that, or maybe we're solving for the distance to the chord. Usually the radius, I guess sometimes we might solve for the radius, but often it's what's given, okay? So this is going to require right triangle, either Pythagorean theorem, right triangle stuff, or right triangle trig if we know the central angle. Because what's true about the central angle in that purple line? What does it do? If you think back to segment solving, that purple line bisects the angle, right? Okay. So maybe put C example. We'll put an example in here, but just so you know the picture. Okay, the one we're not going to write is that if all this is true, then that purple line contains the center. In other words, it's not somewhere else like chord. I can't bisect that chord without going through the center, right? It's not splitting the chord in half, which I think is fairly obvious. So I don't know that we need to write that. let's look at some problems on how these are going to show up. That one's kind of hard, by the way. So we'll come back to it though. Do you like flowers? It's kind of a flower day. It's pretty May, or pretty spring day. Do you think how well do you think you could draw that picture? Obviously the flowers part doesn't have to be there, but do you think we can draw it in your example section?
Yeah.
Yeah, let's do it.
Try.
Just a circle.
Yeah, that's true. Oh, but you know what? Are you? I'll help you out. I was gonna say I don't want you to have to draw all this words, so.
You write all the words.
Huh?
You write all the words.
That is what I mean. Sorry.
Use the word. Huh?
I don't want you to have to write all the words, so let's trim it down a little bit. I did say draw all the words. That's true. Here's really what all those words say. How deep is the water? Probably on yours, I'd recommend doing this, like making the top kind of jagged, like we think of like moving water, just so you know where the level of the water is. All right. So put under here, this is the diameter. So what's the radius?
3.
So step 1 is understand the measurements. What is the 5? Yeah, good. 5 inches is the length of the chord. Okay. I wish we had the theorems next to the problem, but I'll kind of remind you. We had one that said central angle. Sorry, if chords are congruent, central angles are congruent. Is that going to apply here? Do we know any angles? No. Okay. We had one that said if arcs are congruent, their chords are congruent. Is that one gonna apply here? Well, we don't know any arc lengths or measures. Okay, we had one that said if chords are equidistant from the center, they are congruent. Is that gonna apply here? At least we're talking lengths now, right? Lengths of a chord being in terms of distance from center. So it could, except we don't know how far away the 5 is, right? That's what we're trying to find, actually. Okay, so which of the 4 theorems are we going to use? Yeah, the perpendicular one. Okay, so step 2 would be identify the correct theorem. And we probably should put an S in there. You might have to use more than one. Okay, what are we trying to solve for? in the picture? Like, could you draw a line in there or a variable or something to show what we're solving for?
Well, when they're done,
Yeah. Good. Yep. Here's how I want you to do that. Let's call it X, or you could call it D for depth if you want to, but put it on one side. I wrote mine right in the center. I didn't need to do that, but. Just for the example, I'm going to be super clear. But we can break that up into two pieces, can't we? We already know like if we start at the bottom, we already know part of the way, which is called what? The radius, right? And we said the radius is what? 3. So do you see how if we put a center, because all these circles will have a center, now we know that from the bottom to that center is 3. So we already have part of the problem figured out. And so really, what else do we need to know? Like what else would tell us, what else do we need to know the whole depth? If we know it's 3 to the center, what else are we looking for? The center to the chord, right? So maybe put, I don't know, put some other variable right there. Y. Okay, how do we solve for y? That now becomes actually the only thing we have to calculate. Okay, because once we know y, we can just do what with the y and the 3? Just add them together, okay? So how do we solve for y? That's really the question. Before we do that, draw in what you're solving for. Like you just saw in this problem, like none of that was in here. So we had to put all that information in our picture. And then label all you know. So far I've labeled that I know the radius is 3, which is part of the depth. But I can put some more measurements on there. Like what? If you think back to the notes where I said this is the picture that we'll often use to solve, what is missing from that picture? We don't have a 90. Yes, we do. It would be right there where the arrow is by the Y, right? Okay, so we need our radiuses going out here to the ends of the chord. And how long are those? Those are both 3, right? Okay. Next. Zoom in. And that's kind of vague because it's going to be dependent on which problem you're solving. Here's what I mean. So we're zooming in, we're trying to figure out why. How long are each of those?
Oh, that's 3.
No. So remember it said it bisected the chord, right? If it's perpendicular, it bisected the chord. So that means these are both 2.5. All right, at this point, do you see a way to solve for y? Raise your hand if you do. Nice, good job. Okay. So let's finish this note. Zoom in. Draw the focused picture. with, what do we say this, more details, I guess? More detailed information. In other words, when you start drawing all this stuff into the little circle picture, it can get too busy. So zoom in, now we can put Y clearly, the 90 degree, we can say those are congruent and split it in half, like those kind of details start coming out, right? All right. And guys, notes like this are kind of vague because sometimes you run into different circumstances. So you need to be able to think critically. Set up either Pythagorean theorem or trig ratio if you know the angle. Most likely it will be one of those two things. Which one is this? Yeah. Okay, so we're going to set up 2.5 squared plus y squared equals 3 squared. And can you do 25 squared? Or 2.5 squared, excuse me. Thanks. And then will you square root that? Seven? No, square root of 2.75. Just plain 1.6? Alright, so what is the total depth of the water? And we're not going to add a step for that because that's totally dependent on the problem, but we can go ahead and finish it. Well, we were 3 to center, and then 1.6 more from there. So 4.6 inches of water. Circle problems can be involved, can't they? Because we have to use some kind of circle theorem to set up some kind of triangle often, and then use lots of triangle knowledge to solve it. So that's pretty typical. What is that? Is that a 5?
Yeah.
Alright, cool. So we're not packing up yet.
It's not pretty.
Let me know when I can go back to the other slide. Alright, you saw this one. Do you see a similar kind of scenario? The problem, I'll let you do this next week, but the problem says, like, will the trucks fit through the tunnel? Or are they going to crash right here? But do you see how it's a lot similar to the depth of the water? Kind of, okay? Here's some just plain math, where we just have various theorems shown and we're trying to solve for things. So those kind of a little bit less involved. Anybody ever ridden a water slide with, these are tubes. I know they kind of look like blood cells, but it's tubes. Yeah, so, like how deep is the water? That's what this one is going to ask. When you go down. Oh no, she's solving for the diameter when the depth is 2. So how big should the pipe be so you don't have people scratching their bums on the bottom? Okay? So this is cool stuff, right? It's pretty useful stuff. Anybody ever seen radar?
Oh, I have seen one of those.
Yeah.
They look like video games.
So you can see this, you're packing. This airplane is flying through the radar, creating some kind of chord. We'll have to read more about it, but bunch of packers.